A standard Java program operates in a predictable sequential flow. Instructions execute one by one, tracing a linear path through the logic of your application. However, software faces two primary threats. The first is an unpredictable runtime error, like a failed network request, that shatters the sequence and halts the application immediately. The second threat is a performance bottleneck. A single instruction path utilizes only one CPU core, leaving the parallel processing power of modern hardware untouched. Enterprise applications must resolve this paradox. The code must be robust enough to survive anomalies while executing multiple parallel paths to remain efficient. Java engineers use two distinct mechanisms to manage this execution chaos. Exception handling protects the sequential flow by isolating errors and routing the program around them before a crash occurs. Multithreading maximizes performance by breaking the sequential paradigm, allowing different tasks to run concurrently across available processor cores. The complexity of these systems is not found in creating threads, but in maintaining data integrity when multiple threads attempt to access the same shared memory. Understanding how these two architectures interact is necessary for building reliable, concurrent software. Every exception descends from throwable, splitting into built-in and user-defined exceptions. Under built-in, unchecked exceptions, like arithmetic exception, result from logical errors manifesting only at runtime. Checked exceptions, such as I/O exception, represent environmental failures, forcing developers to provide compile-time handling logic. Exceptions are distinct from errors, such as out-of-memory error. Errors represent irrecoverable system states that are generally outside the program's control. This hierarchy forces developers to explicitly account for predictable environmental issues while the application is still in development. A try block monitors risky instructions, generating an exception object if an error occurs. This object drops through ordered catch block filters, from most specific to most general. Only the first matching catch block executes, bypassing the rest. The finally block is used for code that must execute regardless of whether an exception was thrown. This is typically where shared resources, like file streams or network sockets, are released. While the throw keyword is used to generate an exception manually, the throws clause signals in a method signature that a specific risk exists. This cleanly separates primary business logic from error recovery code, resulting in readable, stable applications. While exception handling stabilizes a single path, multithreading allows multiple tasks to run concurrently for maximum CPU utilization. A Java thread begins in the new state, transitioning to runnable once start is called. It's now ready, but only moves to the running state when the operating system scheduler allocates it processor time. Threads are created either by extending the thread class or by implementing the Runnable interface. Implementing Runnable is generally preferred in enterprise systems because it provides more flexibility for inheritance and makes it easier for multiple independent threads to seamlessly share the same data object. Concurrency requires this precise lifecycle management so the JVM can accurately track each independent execution path. A race condition occurs when two unsynchronized threads attempt to modify the same shared variable simultaneously. This often leads to data corruption and inconsistent results. To prevent this, synchronized blocks use an object monitor lock. When one thread enters, it acquires the lock. All other threads are forced into a waiting state until the lock releases. For example, using synchronization ensures that two threads will print their sequences in a perfect, orderly line rather than a scrambled mix. Synchronization is the primary mechanism used to maintain data integrity when multiple threads must interact with the same information. Threads often need to coordinate through active communication. The wait method allows a thread to pause execution and release its lock, letting other threads proceed. The notify method is then used by the active thread to signal that the waiting thread should wake up and reacquire the lock. In a chat program, these methods allow question and answer threads to alternate perfectly, creating a clean dialogue by passing a flag back and forth. Using wait and notify turns chaotic parallel execution into a structured, perfectly coordinated sequence of operations. Exception handling and multithreading both serve as essential tools for managing the flow of a program under different types of operational pressure. Exception handling provides the stability needed to survive environmental failures and unexpected inputs. Multithreading provides the performance required by modern hardware, but it demands synchronization to maintain data consistency. The central challenge is designing systems that can leverage parallel execution, while ensuring that every micro-level operation remains safe and predictable. Balancing robust error handling with the advantages of concurrent execution allows Java applications to remain stable even as they scale for enterprise workloads.